So let me remind you where we were. So last time we proved these things that I'm going to put in a table now. So we talked about graphical matroids, linear matroids, transversal matroids, and gamoids. And for each one of these, we wanted to know whether it was closed under minors and closed under or closed under duals. And so we finished filling out this table last time. So remember that graphical matroids are closed under minors because we have these operations of deletion and contraction in a graph, but not under duals, because you proved in the homework that the dual of K5 is not a graphical matroid. We saw that linear matroids are closed under minors and closed under duals. This was deletion and contraction in the vector configuration, and this was going to the orthogonal subspace of a subspace, the orthogonal complement of a subspace. We saw that transversal matroids really don't behave well under either one of these operations. Okay? And that's why we expanded them to this class of gamoids, which was the smallest class that contains transversal matroids and is closed under minors and is closed under duals. Okay? So this is where we were. And now the question is really, who cares? Who cares about this? Why should we care whether a collection of matroids is closed under minors, closed under duals? Why should we care? Why is this a good thing? Okay. And there's kind of the obvious answer that, we defined minors and we saw that minors are a very, very natural operation. We defined duals and we saw that duals are a very natural operation. And it's nice that our classes that we care about behave well under these operations. So the first answer is just that it's just nice. But the second answer, and the one that is more important to us, is that this is going to be useful as far as understanding these classes. It's useful because it'll help us understand these families of... What I want to show to you is that because I have yeses here and here and here, that lets us understand these three classes in a way that we cannot understand transversal matroids because there's a no here. Okay. It'll help us understand these classes. Okay. And I think that by now, the most familiar to you are these graphical and linear matrices, and I'll start by showing you what this tells us about graphical matrices. And the big question that I want to talk about today, which was a very natural question that we have wondered about since we started this class, is if I give you a matroid, how do you know if it's graphical or not graphical? So how do you know if a matroid is graphical? Whether a given matroid is graphical. Okay. In other words, I give you a matroid given as an abstract collection of whatever I want to give you. I could give you the independent sets, I could give you the rank function, I could give you the circuits, but I give you an abstract description of a matroid, and the question is, can you find a graph that this matroid comes from? Okay. this is what we will talk about for most of the class today. Okay. And so there's two questions involved here. The first one is, how can you tell that a matroid is graphical? And the second one is, how can you tell that it's not? So if it is graphical, then what's going to happen? I basically give you your collection. For example, I give you the circuits. And so, for example, let's say that I give you this collection. I tell you that the ground set is 6. The circuits are these. And I ask you, is this a matroid? Are these the circuits of a matroid? And then what you would try is to draw a graph that has these as its circuits. And so you need a circuit 2, 3, 4. So you could draw it in any way. 2, 3, 4. You need the circuit. Then you need a circuit 2, 3, 5. And the only way that you're going to be able to build it is by putting an edge 5 here. That gives you the second circuit. Then you're supposed to have a 4, 5, and you're lucky that you already have it, so you don't have to worry about that. Then you need a circuit for 6, and you can put it anywhere, maybe hanging from here. And that's it, except that you're missing an element of the ground set. And you can just tag it along anywhere, but make sure that it doesn't form a circuit. Okay. And so there it is. That's how you tell if you have a matroid. You just build the graph. Kim, question?
So this works if it's graphical and it's planar. But oh, I see. You can still crisscross things.
Yeah.
Okay.
This one happens to be planar, but I could give you a list of circuits of a non-planar graph, and you just draw it and you allow the edges to cross.
Okay.
I didn't forbid you from letting the edges cross. So if it is graphical, then what you do is you just find the graph. Now, I'm not saying this is easy. I mean, it's easy in this case because I give you a short list, but if I give you a very long list, then you would have to do this in a smart way. And there's algorithms for doing this, which, if you're interested in, I can point you to the literature where they actually do this in a somewhat efficient way. But I think the harder question is the other direction. What if it's not? What if I give you a matroid and it happens not to be graphical? Then how are you going to convince me of that? Or how are you going to convince yourself of that? Now, let me ask you something. Have we faced this question before? When? So remind me, which was the matroid that you proved was not graphical? So the dual matroid of the dual matroid to the matroid of K5 is an example. This one is an example. Do you remember any other ones that we did? There was actually another one in another one of your homeworks, maybe the second assignment, where I asked you to figure out which uniform matroids were graphical. And you proved there that, for example, the uniform matroid 2, 4 was not graphical, or the uniform matroid, almost none of them were graphical, if you remember. The only graphical ones were kind of the trivial ones, but this was not graphical for m bigger than m plus 2 and m bigger than 2, and this is what you proved in your homework. Okay? And if you remember the proofs of these things, they're totally different from each other. So I gave you this as a homework question, prove that this is not graphical, and I gave you the hint. If you get stuck, go see how Oxley did it, and you saw that his proof is a pretty clever one, and it's not one that you can just think of immediately. I posted on the course website a proof that one of the students in Colombia did of this. which is also very nice, but it's also a very clever proof. It's not something that you could just sit down and think of it right away. For this one, it was also a little bit of work, and it was in a completely different way that we solved this, that you guys solved this question. Okay? And so the question is, how can I treat this in a systematical way? And yeah, how can I answer this question in a systematical way? Okay? So, for example, let's say that I give you this collection. Maybe I'll leave this here. Let's go over here. And I'm going to give you a collection of things that goes like this. 1, 2, 7, 9, 1, 2, 8, 9, 1, 3, 4, 5, 6, 1, 7, 8, 9, 2, 3, 4, 6, 2, 5, 6, 7, 2, 7, 8, 9. Okay. A bigger list. And let's say that I ask you, is this a graphical matroid? Are these the circuits of a graphical matroid? Okay. And you're going to stare at this and probably not know what to do. Okay. And you might start by trying to draw the graph. That might be the first thing that you try. So maybe the first thing you would do is draw a circuit 1, 2, 7, 9. But already by drawing that one, you lose generality. Because it could be 1, 2, 7, 9. It could be 1, 7, 2, 9. And those are different cases. And that's only for the first one. And then you have to make sure that the second one is a circuit, the third one is a circuit. And there's going to be a million cases to consider here. This is not what you want to do, right? So I'm going to show you how I can tell that this is not a graphical matroid. Okay? Well, suppose it is. Let's call it M. Okay. Now what I want to do, I didn't tell you the ground set. Let's say that the ground set is all the numbers from 1 to 9. These are the circuits. And let's suppose that this is a graphical matroid. Okay. Now I'm going to take this matroid and delete the elements 3, 4, 5, and 6. What are the circuits of this matroid? You'll see.
General cleverness.
I mean, this is the first time that you see this argument, and so it's going to look very unnatural. But then when I'm done with it, you'll see what is the kind of thing that you want to do in general. Okay? So basically, what I did is restrict to 1, 2, 7, 8, and 9. Okay. And so what I need to do is look at the circuits here that only involved those guys. 1, 2, 7, 9, 1, 2, 8, 9, 1, 7, 8, 9, 2, 7, 8, 9. Okay? And now I try to understand the structure of this matroid, and I realize something funny about this matroid. What do you notice here? Is there a special element? 9 is everywhere, right? 9 is a loop of this matroid. I mean, 9 is... No. It's not a loop of this matroid, but 9 is in every circuit. And so let's delete it. I mean, let's contract it. So let's take this matroid and now contract 9. So what are the circuits of these guys? Well, they are the circuits that involve 9, and now you collapse the edge 9. You contracted it. And so what you're going to do is just take all of these guys and remove 9. And you get 1, 2, 7, 1, 2, 8, 1, 7, 8, 2, 7, 8. And I get a matroid where these are the circuits. Do you know this matroid? Does it look familiar? What is the ground set of this matroid? 1, 2, 7, 8. Okay. If you look at these circuits, they are all the sets of size 3. It's the uniform matrix, exactly. The things of size 3 are dependent. The things of size 2 are independent. So this is the uniform matrix where every 2 guys form a basis. So what I showed is that if I delete 3, 4, 5, 6, and I contract 9, I get the uniform matrix U24. Okay. And now I claim that I'm done. Why am I done? Because I assumed that M was a graphical matroid. And I know that graphical matroids are closed undertaking minors. So if M was graphical, then when I delete things and I contract things, I still should have a graphical matroid. But you guys proved in your homework that U24 is not a graphical matroid. Not graphical. And therefore, this is a contradiction. And what that shows is that my matroid, that these are not the circuits of a graphical matroid. Okay. There's my proof. Now, what's the philosophy here? The philosophy here is that whenever you have a graphical matroid, every matroid that is living inside it is graphical. That's what minors mean. Minors are the matroids that live inside the matroid, right? So if I give you a matroid, and you manage to find a matroid inside it that is not graphical, then that shows that the one you started with is not graphical. Okay. And this is going to happen whenever you I mean, in this case we found U24, but you might have found this one. If you find this matroid living inside a matroid that I give you, then you know it's not going to be graphical. And the crucial property is that graphical matrices are closed undertaking minors.
So these are the ones that we currently know how to go after. Mm-hmm. Are there a bunch more out there that...
That's exactly the right question to ask. So is this the complete list? I mean, are these the only things that could go wrong? Or are there more? Well, you guess not.
Sorry, just repeat what you said, Federico. So if you have any graph who has a subgraph that's one of those three,
then that means you didn't have a graph to begin with. Okay. So if I give you a matroid and I ask you, is it graphical? If you happen to find one of these guys living inside your matroid, then you know that the big one is not graphical because everything that lives inside a graphical matroid is graphical. And so maybe the reason you guessed that there are more is that you saw me switch to that board and not and I start writing here. This is not the end of the list. So some non-graphical matroids. Non-graphical matroids. Here's one, here's another one, here's another one. And there's another question that you should be asking me, or asking yourselves. What are you going to ask?
No, I was going to say, it seems like a more general strategy that's rather than trying to find one we've already proved, is you can just maybe try some different minors and reduce it down to something that's much easier to prove is non-graphical, as opposed to trying to necessarily find one of these.
Sure. So what Chris is suggesting is that another thing I could do is just start with a big matroid that he wants to know is it graphical or not, and then just reduce it to a smaller one, where maybe this smaller one is more manageable. Okay? It depends how bad this list is. If this list is short, then maybe you just want to look for. I mean, if this was it, then maybe you just wanted to look for these three guys. If this list consisted of 20 matrices, then probably you don't want to go looking for all of them.
So I guess for any size ground set, you're only going to find out the use of and then
So this is the question that I meant you should be asking yourselves, is also whether this is a redundant list. In other words, does U24 live inside this guy? Because if it does, then I can get rid of this guy. Or does U24 live inside UMN? That seems plausible, right?
Well, U24 is just an example of it.
But for example, does U24 live inside U700 1997? So we know that this guy is not graphical. Is it because there's a U24 in there? Well, what happens when you take a uniform matroid and you delete an element? So you had a matroid of n elements where any m of them are a basis. Now you're deleting the element e. So what that means is you're forgetting e exists and you're just looking at the bases that don't contain e. So how many elements does this new matroid have? N minus 1. And how big are the bases? M. Because the bases of this matroid are the bases of the old matroid that don't contain e. So you lose some bases, but the bases of these guys are all bases of UMN. Okay? So when you delete an element, you just get a smaller uniform matroid. What happens when you contract an element? Then you get a matroid where you have n minus 1 elements. And what are the bases of contracting? Remember, what you do is you take the old bases that contained e, and you delete e from those. So those bases had size m. Now they have size m minus 1. Okay. And what that tells you is that um minus 1, n minus 1 lives inside umn, and umn minus 1 lives inside umn. I think that's a pretty good indication that U24 lives in here. So how many things should I yeah, what should I do? What should I delete? What should I contract?
Contract.
We want to
Delete 9,993 of them.
I can't think up here on the board. I'm just going to say I'm going to delete A and contract B. What are we going to get? So the ones that I deleted, how many times did this guy go down from m to n minus 1? The number of times I contracted, B. And how many times did
A plus B.
this guy go down? A
Minus B.
B. So what I wanted is B equals, I want this guy to be a 2, so 698. And I wanted A to be, it's impossible. 1997 minus 698 is 999. So I want 995. It's the hardest thing we've done today.
Perhaps all here.
And it might be wrong, I don't know.
698. It's
No,
not
it's
999.
not. It might be something like
Maybe like
1299.
1295. Now, the point is that you could do this for any number that I put here and any number that I put here in this range. So actually, these guys I don't need to put on my list because U24 lives inside all of them, and so that's a good thing because I don't want an infinite list. I mean, this would be useless if I give you an infinite list here. Okay. Not useless. It's useful. It's useful conceptually, but in some cases it's going to work, but in some cases it just makes it harder to use.
Or if you have infinite families.
Sure.
You could, if that was an infinite list, as long as you find the uniform figure somewhere. That's nicer.
Now, maybe I'll say two things about this. So first of all, this is very useful, as I showed you, for proving that matrices are not graphical. But not only that, I think the thing that you should take from this is that if I manage to make a list like this, then these are the reasons why a matroid could possibly not be graphical. And therefore, I think that Chris's suggestion, even though it makes perfect sense, I think in practice you just want to boil it down to these, because the argument that you would make on the bigger matroid is going to be one of the 5 arguments you would have made here, or 7, or whatever this list is. Just gave it away that there's 5. There's 5 guys on this list. There's 2 missing. And I'm sorry? Yeah, I'm not claiming this was easy, but I'm claiming that it's a proof, and it's somehow, at least I know what I'm looking for. I'm looking for a U24 inside it. But the point is that there are 5 reasons why a matroid is not graphical, and these are the only 5 reasons. So let me show you another one of the reasons. Okay, I'm going to introduce you to a new matroid called the Fano matroid. F-A-N-O. Okay. People like to draw this matroid in this way. And I'll explain to you why. So you're going to imagine that the elements of the matroid are these 7 points. And wherever you see a line or this circle, that's a circuit. Okay. So this is A, B, C, D, E, F. Then my ground set is this G. So there's 7 elements of this matroid. And the circuits are the lines that you see. So A, B, C, C, D, E, E, F, A. Then these diagonal things, A, G, D, B, G, E, C, G, F, and then the circle, B, D. Okay. So is it clear how I'm getting these circuits from this picture? I should tell you that in a lot of the matroid literature, when people draw a matroid for you, they just draw a picture like this. And you're supposed to imagine that whenever you see things on a line, then like C, D, E is going to be a circuit, and so on. Okay. So there's a matroid, but we don't know that yet. Okay. We don't know that yet because I just gave you a collection of circuits, and not any collection of circuits is a matroid. And we saw that there's different ways of going about proving that something is a matroid. So one thing you could do is just check the circuit exchange axiom. Okay. So for any 2 circuits that intersect, you have to find a third one. You could do that. Okay. It's going to take you a little bit of time, but you can do it. And the other method that we have seen for proving that something is a matroid is showing, well, I knew this matroid already. I've seen it before. And so that's what I'm going to do with this one, is I'm going to show you that actually this is just a linear matroid. Okay. So I'm going to construct a representation for you. And by constructing a linear representation, we'll see that it's a matroid. Question?
I should have stopped you a little bit earlier. I am kind of curious about that diagram and how ABC can be a circuit. Yeah, I'm seeing ABC, and it doesn't look like a circuit.
So you.
Is it that was a graph?
Yeah, the thing is, you should think of this picture as a new way of drawing matrix. So this is not meant to be a graph. This is not meant to be a. This is not meant to be a lattice of flats or anything. This is just a representation that people like to draw so that they don't have to write out this list. Okay? And this tells you a little bit about the combinatorial arrangement of this. I mean, if you look at this, you don't see any symmetry in the list. But if you look at this picture, you see that there is some symmetry in the circuits of this matrix. But this is just a visual aid. This is not meant to be a graph. Right? Okay, linear matroid. So I'm going to define a vector configuration for you. But this is the first time that I'm going to have to do something a little bit funny, which is not work over the real numbers. So far, we've worked over the real numbers every time. But here, I'm going to use a vector space over a different field. And the field that I want to consider is a much easier one than the real numbers. It's a field of 2 elements. This field has 2 elements, 0 and 1. And well, you know how it goes. 0 times 0 is 0. 0 times 1 is 0. 1 plus 0 is 1. But the key difference is that 1 plus 1 is 0. And believe it or not, this is why I want to do this. Because 1 plus 1 is 0. That's what I want. My vector space. Now the point is this is a field. And I think all of you have all of you seen field theory to some extent? I mean, you have to check the actions of a field. This is the multiplicative unit and so on. The vector space is just going to be f cubed. So you're just going to consider the things in 3 coordinates where each coordinate is 0 or 1.
What's your GEF notation? I've never seen people write that.
I wrote it like this because this is how Oxley writes it. So, this is just the field of 2 elements. And I'm going to show you a vector configuration. And the vector configuration is going to be, well, you see you're pretty limited here because how many vectors are there here? And this is a vector space that only has 8 vectors. Right? The first coordinate is 0 or 1, the second one is 0, 1, the third one is 0, 1. So you don't have a lot of choices for your vector configuration. And if I force you to pick 7 vectors, which ones would you pick? All except for 0. So you're going to pick all of the vectors except the 0 vector. Okay. How can I draw this? Well, it's a cube. You can picture this as a cube. So let's say maybe this guy is 0, 0, 0, and maybe I should be consistent with the way that I drew it here. So I say that these guys start with zeros. Then so this is what f cubed looks like, and so these are the 8 vectors in the vectors. Did I do it wrong?
No.
Okay. So this is the origin, and then the 7 vectors that I'm considering are this one, this one, this one, this one, this one, this one, and this one. Okay. Now, I'm claiming that this vector configuration is supposed to match this right here. So what I need to do is tell you which vertex corresponds to which vertex here. I think if you look at it, there's kind of a natural way of labeling these guys so they look like these, which is to call this guy A, go around, A, B, C, D, E, F, and this guy G. Okay? And what I'm claiming is that the linear dependencies of these guys are exactly the circuits of these guys. Now, what's a linear combination in this vector space? Well, the only scalars are 0 or 1. Okay, so a linear combination is just a sum of vectors. So you have a linear dependence when you have vectors that add up to each other, that add up to 0 rather. Okay. So for example, ABC is supposed to be a circuit. Well, if you add up this vector, and this vector, you get 0. Yeah? And I mean, geometrically you see it, that they're on this plane, and that's why they're dependent. And so, you know, for example, this AGD tells you that A, G, and D are collinear. They're in this plane over here.
So
I'm
what's
sorry?
so special about the field that we're over then?
Does anybody see why I need the field of 2 elements?
1 plus 1 is 0.
See that?
And also that you can only have scalars.
But
But they're all on the same.
there's something funny about this configuration, which is this circuit, BDF. And I'm claiming BDF is a circuit here.
Yeah.
Why? Because if you add 1, 1, 0 plus 0, 1, 1 plus 1, 0, 1, you get 2, 2, 2, but that's 0, 0, 0. And that's where I need it.
But you're getting that for all of them.
No, but all the other ones would still work over.
B plus D plus F is 0. I mean, because, right, A, F, and E are linearly dependent over any field. A plus E equals F. And that's true for all the other relations except for this one. B, D, and F are only dependent if 2 is equal to 0. And this is the key thing. This is why I need to be over GF2. Okay, so that's my proof that this is a matroid because it is this linear matroid. Any questions about the Fano matroid before I continue? So what I want to show now is that this only would have worked in characteristic 2. So if I can represent the Fano matroid in a field, then in that field 2 is equal to 0. So the Fano matroid can now be represented as a vector configuration in over. Let me say the way that people say this: represented over R. And what this means is that it cannot be represented as vectors in a real vector space.
But that doesn't mean that it has characteristic 2.
And so give me just a second. As vectors in R3. And in fact, I mean, I just want to prove it this way, but you'll see that the same proof goes for any field of where 2 is different from 0. So in other words, characteristic is bigger than 2. So that's what I'm going to show. I'm going to show that you cannot represent this matroid over R, so there's no collection of 7 vectors that satisfy these relations. So suppose you can. Suppose it is represented.
And you can, without loss of generality, you can just be in R3 because you have a rank 3 matroid. So.
Right, my matroid is of rank 3, and so if the vector space was bigger, if there was a 7-dimensional space, then I would just cut through the span of the 3-dimensional vectors, and that's isomorphic to R3. So I can just assume that my vectors are in R3. I'm going to show that I cannot find these vectors. Now, yeah?
How do you know, just looking at that you've got rank 3? I mean, I know from the bottom here.
Because A, G, E is a basis. I mean, you have to look. So either you look for, I mean, here you know that it's rank 3 because it's linear in a 3-dimensional space, or here you would have to just convince yourselves that there are bases of size 3 and there are not bases of size 4, which you can do. So suppose it is represented. So I have 7 vectors, and now I can take my 7 vectors and apply a transformation to them so that 3 of them are wherever I want. You can take any 3 vectors in R3 and apply a linear transformation that sends them to the basis vectors. This is just linear algebra. You say send vector A to 1, 0, 0, vector B, vector C to 0, 1, 0, vector E to 0, 0, 1. There's a matrix that will do that for you. So you can do a linear transformation.
Since we know ACE is supposed to be a basis.
Right, then that's important. ACE is a basis, and so they are 3 independent vectors. And any 3 vectors in R3 you can send to the basis vector. You can assume that A is 1, 0, 0, C is 0, 1, 0, E is 0, 0, 1. If you prefer, you can put parentheses and commas. Hopefully that's clear. And let me give a name to the middle guy. I'm going to say that the middle guy has coordinates x, y, z. That one I don't get to choose. I don't get to choose where I put that one. So I just say it has coordinates x, y, z. Okay. So now I want to say this. Look at vector D. Okay. D is a combination of A and G, because ADG is a circuit. So D is a combination of A and G, right? And A is 1, 0, 0, and G is x, y, z. I know that D has that form. But also, D is supposed to be dependent with C and E. So I can write it as a combination of C and E. And C is 0, 1, 0, and E is 0, 0, 1. Okay. So this shows that D has the following form. What is the first coordinate of D? Well, it's a combination of 0 and 0. So the first coordinate of D is 0. And what can you tell me about the second 2 coordinates? Well, if you look up here, these guys don't matter. And so the second 2 coordinates are something times y, something times z. And the same something. So let me call that ry, rz. And I claim that r has to be non-zero. It has to be the same r because they are here. R times y, r times z. And r is not 0 because if r was equal to 0, then d would be the 0 vector. And it would be a loop in the matroid, but this matroid has no loops. And actually, I meant to say here also that you know that x, y, and z are not 0. And why is that? Because, for example, if x was 0, then g would be of the form 0, y, z. So g would be dependent with c and e. But if you look here, you see that g is not dependent with c and e.
So already we're in trouble.
So x, y, z is not 0, r is not 0. Right, none of those are 0. So that's D, and I can do the same for the other 2 guys. So what am I going to get for E? I'm going to get I get a 0 in the middle, right? And then these guys are the same multiple of x and z. By the same reason. So D had a 0 coordinate at first, and then a multiple of y, multiple of z. E has a 0 coordinate in the middle, and multiple of x, multiple of z. And right, S not equal to 0. And F has a 0 in the last coordinate, and then a multiple of x
you mean B for
multiple of y. What did I do?
this B?
B.
That,
Actually, what I mean, let's see which is which. Which one has a 0 coordinate in the middle? It's the combination of this guy and this guy. So it's actually F.
Oh, yeah.
yeah.
F is the guy that has a 0 coordinate in the middle. And the one that has a 0 in the last coordinate is B. And again, T is not 0. Okay? So what have I done so far? Well, I already took care of 6 circuits, right? This is the circuit DAG and the circuit DCE. DAG and DCE. And in the same way I took care of this circuit and this circuit. I took care of all of them except for BDF. I haven't checked that that's a circuit. And it's supposed to be. Right? So BDF is supposed to be a circuit. So let's say that alpha B plus gamma plus beta D plus gamma F is equal to 0. And again, I can assume that alpha, beta, and gamma are not 0. Because if one of them was 0, then I would get a relation between D and F. And I'm not supposed to have a relation between D and F in this matrix. Okay? So let's just write this out and see what we get. Alpha times Tx, Ty, 0. Plus beta times D is 0, Ry, Rz. Plus gamma times Sx, 0, Sz is, when you add all of this, you're supposed to get 0, 0, 0. Okay? Let's look at the first coordinate. I have alpha Tx plus gamma Sx equals 0. Okay. But remember that x is not equal to 0, so I can get rid of it. Okay. The second one says alpha T y plus beta r y is equal to 0. And again, I divide by y, which is not 0, and I get this. And the last one says beta r z plus gamma s z equals 0. And then I divide by z, and I get 0. So what did I get here? I just found 3 numbers, alpha t, beta r, gamma s, such that any 2 of them add up to 0. So this guy is, I mean, how is that possible? You have 3 guys such that x plus y equals 0, y plus z equals 0, and x plus z equals 0. So this one means y is equal to minus x. This one means z is equal to x. That z is equal to minus y. And then this one says x plus z is 0. It says 2x is 0. But x is not 0. So what you just proved is that 2 is equal to 0. Okay. So the only way that this computation could have worked is if 2 was equal to 0, which never happens except in fields of characteristic 2. And there's my proof. Okay?
So you didn't even need to say that thing about R. You could have just stated it.
What thing about R?
The way you stated the theorem, you kind of said it can't be represented over R.
Oh, I erased my theorem. Yeah, I mean, so I proved that it cannot be represented over any field where 2 is not equal to 0. And in particular, not over R. So I showed theorem F7 is not representable over R or any other field that doesn't have characteristic 2. And in fact, there's another matroid that immediately I get is not representable, which is the dual. Yeah? Because if the dual was representable, then this one would be its orthogonal complement. It would be representable. So there are two matrices that are not representable over R.
So that closure under duality actually
So I'm using closure under duality of linear matroids now.
But what you just said
Oh, and
shows an argument that works for a given field.
for linear matrix over a given field.
Yeah.
So if I was able to represent this in R whatever, then this one would be the orthogonal complement in that vector space, which is also a real vector space. Okay? But you'll remember that you proved in the first homework that graphical matrices were representable over R. And remember that the way you did that is you said, whenever I have an edge ij, I'm going to make a vector that has coordinates 1 and -1 in entries I and j. So that was your homework, right? Yeah. So this was in homework 1, I think. So since these guys are not representable over R, and graphical matrices are representable over R, that means that these guys are not graphical. Okay. It is kind of a roundabout way of proving it, but there's a proof.
So are you claiming that every non-graphical matroid has one of those 5 as a minor?
I am. So let's conclude with that. Theorem. This is due to Tutte. I'm in the 50s. 59. A matroid is graphical if and only if it doesn't have one of these minors. And this, in a way, is a huge theorem. I mean, you can imagine that this is one of the big theorems of the field, because it tells you, what a graphs look like in a way. That there are 5 things that stop you from having a graph in your hands. It's a very powerful structural result about graphs living inside matroids. Now, I should say that the proof of this is very hard. It's difficult.